in fluid dynamics, you have Torricelli's theorem, which relates back to speeds of a fluid. One is typically at a higher height, and then the other one is at a lower height, okay, and then it exits. Okay, you can imagine that you have some kind of a dam, and that particular dam's lifted, and you have kind of a fluid which is flowing out. Now, I want you to think about, before we start deriving this, okay, and then what the relationship between the actual two speeds are, okay, relative to the heights, okay, between them. Think back of kinematics. So it is, I hope it is, much easier for you to recall. So if you have, okay, let's say an object, okay, which is at a particular height, okay, and it's being dropped down. So as you are thinking about this, so let's say, you know, you have your initial speed, and this particular speed, so it might be 0, but it might be some particular speed that this object is falling at. Now it's going to be falling at, and there is gravity which is pulling it down, so you're going to have G acting on this particular object, and we're going to assume that there is no resistance, right? So as it kind of flows downwards or falls downwards, okay, there is no resistance, and therefore the gravity would be the acceleration that you have. Now, if you wanted to find out what the final speed is, obviously there's many ways that you can do that. However, one way of doing this is relating it back to a pretty common kinematics equation. So if you know what the height is, so if you imagine, so from this particular point to the starting point, so if you have a height in between here, so I'm going to call this particular height, let's say, you know, maybe delta H, which is the change in height. Okay, so maybe this was, you know, from height initially to height at the end. Okay, and then what is that particular difference, okay, that you have? Now, it turns out that the final speed, okay, squared is equal to the initial speed squared plus twice, okay, the acceleration. In this case, it's g for us. And the actual distance that it has covered. Now that distance for us is delta H, right? So that's what we have in here. Now this is just a regular standard equation for kinematics. When you have an initial speed, you have your acceleration, A, and then you have a change in displacement. So the change in the distance, okay, that something falls. So that's where this is actually coming from. Now I want you to think about this, because this is exactly what Torricelli's theorem actually states for fluids. Now, one of the key assumptions, and in his theorem as well, is that we kind of neglect the resistance, okay, along the way, just as we would have for an object which is falling, okay, through the air. So if we neglect this, you know, we can derive a very nice equation for the actual final speed that we have. So now that I have kind of shown this to you, and hopefully you remember this from kinematics. Now, if you don't, okay, so I can kind of relate back to the key equations of kinematics up on top there, so if you can take a look at that. Now, if you take a look at fluids, and fluids in particular, this is typically studied in dynamics. So if you take in, and this is, I'm going to try my best, okay, so within here, so let's say that we have some kind of a fluid which is being constrained. And this particular fluid is being constrained, okay, in here. So it's going to be on the left-hand side. We will have an opening in here, so at the bottom, right there. And so I'm trying my best here, okay. So this is, you know, hopefully you'll see what I am trying to draw here in just a moment. So let's say that, you know, we have a fluid which is on the left-hand side here. And this particular fluid, all right, so this is all the way at the bottom, right? So this, all of this is, you know, contained within a fluid. You can think that it's water. Now, this particular fluid is going to start flowing out, okay, from here if there is an opening. And really what Torricelli's theorem wants to kind of ask about is the following. So if we have, so all the way at the top, right? So if we have in here, so we have some initial speed that this particular fluid is at, and it is at a certain pressure. Now, for this particular case, the pressure is actually going to be the atmospheric pressure because it's right at the top, right? So we have the atmosphere all the way around. And what that means is that this particular atmospheric pressure is going to be everywhere over here, right? So this means that it's all over the place over here, which also implies that you have your P atmospheric all the way over there. So this is also at the atmospheric pressure, okay, at the exit point. Okay, we have our final, okay, speed of the fluid, which is going to, flow out from here. So it's going to be kind of going in and flowing out, okay, as it goes through. I guess it doesn't really go upwards, okay, but the ones from the top. So I have to be careful there. So what we have is something like this. All right. So now the question arises, what is exactly this final speed in here, right? So that's what we would want to be able to figure out. Well, we can take a step backwards, and in our step backwards, we can think about Bernoulli's equation, right? So in Bernoulli's equation, we have the relationship between pressure. We have a kind of kinematic term with regards to the speed of a fluid, and then we have an actual potential term related to the height, okay, that fluid might be flowing at. So within here, as you can see, so I'm going to, just for the sake of convenience, okay, in here. So let's imagine, okay, so we have this particular height, which is all the way to the top of the fluid. So this, I'm going to kind of just shift over here, just so that you can relate it back to what I'm drawing. So this, let's call this, our initial height. And then we have, of course, our final height, okay, so this is going to be right there. And this is going to be height number F, okay, or height number 2. I'm going to call it just F for the final because I designated this as my final speed in here, right there. So we do have a difference, right? So we have a difference between H1 and H2 in here that you're going through. All right, so now let's take a look and see what will actually happen here if we're relating it back to Bernoulli's equation. So in Bernoulli's equation, so let's take a look at all of these. We have a pressure, we have a particular speed, it might be 0, and then we have this at a certain height. So what that tells us is that we will have, so P atmospheric, okay, plus, this is from Bernoulli's equation, 1/2 times the density, right, of the fluid itself. It could be water, I'm just going to leave it at density for the moment. And then times the actual speed, so this is going to be VI squared. And plus, and this is going to be coming in from the term related to the fluid at a particular height. So times G, okay, and then times H, and I'm going to call this HI right there. Now, we know that this is equal to a constant from Bernoulli's equation. So if this is equal to a constant, that means that all of these, so if I have the pressure at the bottom, the speed, okay, and then the height, they should be equivalent, right? So that means that I can again write, I'm going to write this out in red just so that it distinguishes it back from the left-hand side. So we have our pressure, while our pressure is still atmospheric pressure right here, so that's that. Plus we have the term which is related to the flow, which is the speed of the fluid, so that's going to be that right there. And then we have the actual height related back to that kind of potential energy, okay, that we have per unit volume, and that's what we would have in there, right? So we have left-hand side and the right-hand side. Now, if you've forgotten about Bernoulli's kind of equation, I can put up a link up above there for you, right? So if you want to kind of get a gist of what Bernoulli was talking about. All right, so now that I have all of this, notice something really nice happens, and that is, okay, so this term right here, which is the pressure term, I also have the same term right here. So these two terms are going to cancel each other off, right? Because if you bring it to the left-hand side or the right-hand side, then P atmospheric minus P atmospheric is just going to be 0. So that is all gone, and we don't have that anymore. Now, once you do that, something else very interesting happens. Notice that all of a sudden, I have density, which is basically in every single term here. So we have density in every single term once that pressure term is gone. So I can technically divide by the density on both sides, and it's going to get rid of that density entirely. So all of these densities are going to fall off on their own because I have them in every single term, and I have them on the left and on the right. So I can just say, okay, well, let's divide both sides by the density, and therefore this is all gone, right? So this is now finished and out of there. And now all of a sudden, okay, what remains, it's very interesting that we have now VI, this is squared, plus, and this is going to be, G, And I'm sorry, there's a half term right there. So g, and then this is my hi right there, which is equal to, and again, 1/2, this is my final speed, plus the g that I have in there, and times the final height. Okay, now I want to be able to solve, right, this thing right there, because that's what I'm after. I'm trying to figure out what that speed is. That's what Torricelli's theorem is all about. So now all of a sudden, okay, I can bring this term over to the left-hand side. So I'm going to do that. And therefore, so this is going to leave me with this. I'm going to duplicate it. That's on the left-hand side right there. Minus, and this is the other term, which is going to be my g, and then my final height right there. This is going to be 1/2, and then vf squared. Now, notice what happens in here. So what I have is 1/2, v I, so the initial speed, plus, now notice I have a g and a g in here. So what I'm going to do is I'm going to kind of factor this out. So this is going to be g, and then this is going to be hi minus hf, which is equal to 1/2 vf squared. But hold on a minute, right? This is just the difference, right? So this is the difference in height. So if I go back in here, really this is just this, right? Because it's hi minus hf, so this is kind of like your difference in height that you have in there. So that's what you would have right there, which now simplifies my equation so that I have, which is 1/2 vi squared plus all of this. Now, of course, since I wanted to be able to find out what this is, I can now multiply both sides by 2, so to get rid of, this half right here. And if I multiply this by 2, then all of a sudden this half is going to be gone, because 2 times 1/2 just leaves me with vi squared. The 2 is going to come up in front right there. And look what happens. And this is actually Torricelli's theorem. So what we have is, we have that the final speed of the actual fluid, and again, so this is below some certain height, okay, from the top right there, is equal to the initial speed, and then times all of this that you would have. So that is pretty neat, right? So if you're having this all the way through, if you wanted to find out, and this is of course related back to the top, right? So this is related back to the top, and we played a key role here that these two pressures were actually identical, right? So that's what would have happened. And then, we can find out, all right, so what is the actual speed? Sure, we can take the square root and find out what that answer is. Now, if you look at this and compare it to exactly what I started about a falling object, right? So in a falling object right there, so notice, this is exactly the same equation, right? You have your initial speed twice times the gravity times the delta H if you were only referring to, okay, an object without, again, resistance, kind of falling down. And there you have it. That's how you can derive this particular theorem. Thanks for watching. See you in a future video. Bye, everybody.